Yeah, here we go. Actually, I just prepared one study material for basics of water supply design. Okay, so you can see the table of content with introduction to water supply design, then the water demand estimation, water supply design, plumbing system design, hot water supply system, then the cold water storage and transfer system, design calculation and work examples. Then there are some standards. Okay, so this one I just prepared based on physics. Like whenever you talk about fluid, it based on the physics explanation. So I just prepared based on that. So you will find there are some equations like you can see like Bernoulli's equations. Okay, for the hydraulic head, some explanation. Okay, we will go in detail step by step, but just for understanding. Then there is a water demand and water supply friction unit. Okay, so basically it's based on probability probabilistic theory. Okay, so it's not based on peak. Okay, so it's not like based on water chilled water system. This is based on the water supply is based on probabilistic theory. Okay, so here are some definitions, equations. You can see the diversity factor, peak factor, storage volume, everything is given. Okay, some explanation. Then the pipe design and friction, how we calculate velocity, pipe sizing formula, Darcy Weisbach equation. There are some equations I have given. Uh, we will be using all this type of equations in our when we do the calculations. Okay, so the NPSH calculation, hot water system, the cold water storage, worked example, everything. Okay, based on that, we prepared some study material around the 42 pages. You can go through. So first, when you talk about introduction to water supply design, so the objective is adequate flow supply. Okay, whenever you use pictures like wash basin or WC or shower, whenever you use, you should get adequate flow supply. Okay, so the flow must satisfy average demand, peak demand, and simultaneous usage pattern. Sometimes it will be average. Okay, like if you have a 10 toilet, maybe some people will be using, here and there. So that is like average. And peak demand is nothing but maybe sometime all 10 people will be using it. So that also you have to satisfy. The simultaneous usage means at the same time they will flush the WC or they will use the shower. Say for example, 10 showers are there. Maybe they will be using 10 showers at a time doing some peak application. So we should satisfy all this adequate flow supply. Then adequate pressure, that is very important. Okay, you will get flow but not pressure means it cannot satisfy. So the flow and the pressure should satisfy. Okay, so the reliability, the water quality also ensure potable water meets chemical, biological, and physical standard. That is why every water supply system we use the treatment like chemical. There is a filtration or you have a treatment system. Okay, then also we will talk about energy efficiency. Like whenever you design the system, should be it should be with optimized pump selection. Okay, so the selection is based on proper pipe sizing, proper flow calculation, everything. Okay, here you can also say some physics perspective on flow and pressure. This is the equation. Like a piping system is a fluid energy distribution system governed by conversion, converse, conversation of energy. Okay, so here you can see some equation P by rho g plus V square by 2g plus S equal constant minus HF minus HM. So here there is a definitions. Okay, rho water density, flow velocity, elevation, friction. So whenever you do the pressure drop calculation or pump head calculation, you'll be using based on this. Okay, so the component of water supply system basically there is a water source. Okay, so the water comes from where? Uh, from wells, bore well. Okay, and you can say the surface water comes from rivers, lakes, reservoir. Okay, so here the depends upon the different system. You need a different type of treatments. Okay, so there are some solid particles. Sometimes there is a biological growth. So to analyze the water, available water, then based on that you can able to treat or filtration. Okay, then you can see the storage system. The purpose is to balance daily consumption and peak demand. Okay, say for example, if you talk about in Middle East, normally we go with 1 day or some application 2 days. Okay, but if you go to some other countries, maybe they may require 6 days, 1 week storage, sometimes 10 day storage. Depends upon the availability. Okay, so here you have a physics principle, hydrostatic pressure, P equal to rho g h. Okay, so the h is the elevation, so the P is the pressure. Okay, so the tank sizing formula will be V tank plus equal Q P plus retention. There will be some amount of water should be in retention all the time. Okay, like the dead area. Okay, so they ensure sufficient water for peak hour consumption. Then the distribution network by means of HDPE pipe or GA pipe or PPR copper. Okay, you have a different materials with fittings like elbow tees, reducers. Then you can see hydraulic equipment, pumps, PRV, surge tanks. Okay, so this is the flow continuity equation. Q equal to A multiplied by V. So this is normal equation, but whatever we use, whenever you calculate the flow rate, A area multiplied by velocity, okay, to determine flow rates. Then for the energy loss calculation, see for example, whenever the flow pass through the pipe, there is some losses due to the friction. Okay, so that friction loss we calculate by using Darcy-Weisbach equation, which is F LV square by D 2G. Okay, so then the minor losses by these equations. Okay, so you can see the velocity limit for the branch pipe 0.6 to 1 meter per second, and for the main riser, normally you can go with 1.5 to 2 meter per second. Okay, then the pumping system, can you see the total dynamic head? The head T dynamic is nothing but head static. Okay, so say for example, whenever you calculate the head dynamic head, you have to calculate the static. Static means from the lowest portion to at what level it is going to distribute. So that is called static height. Then the friction through through the pipes, through the valves, everything. Okay, so here the pumping power requirement. If you want to calculate the power, so here there is the equation P equal rho G Q heads divided by efficiency. So you want to calculate pump power. Okay, by using this equation you can calculate. Okay, here there is a NPSH, suction conservation. Why we calculate NPSH? To avoid any cavitational. Okay, if there is any cavitation, it will affect your say for example your blades of the centrifugal fan. Okay, or your component or your internal the centrifugal pump, it may the cavitation, it's like a bubbles. Okay, it's air bubbles. It may go and hit on your damage on your equipment. It may damage. Okay, so that is why we calculate the NPSH as well. Okay, then the special equipment like that is filters, water softeners, UV sterilizers, PRVs, air valves, such tanks. Okay, also you can say like water hammer arrestor. There are a lot of it. Okay, then the water quality consideration is based on health, performance, and hydraulics. Okay, so the physical properties like sometimes you have to check the color, temperature. Okay, turbidity. Okay, so high turbidity increases friction and reduces effective diameter. So you have to check that physical properties of the water. Chemical properties like hardness, pH, dissolved salts. These are chemical properties. Hot water scaling reduces internal diameter, increase velocity, increase RE, then increase friction factor. If the friction factor increase, then your pump power will increase. So then the other one, biological factor. If we have any bacteria, algae, viruses, contamination may require disinfection and filtration, which adds minor head loss. So these are the things we have to calculate. So this is the equation for viscosity, V equal rho by or mu by rho. Okay, so this calculates viscosity. Then there is a density. Small variation affect pressure head and pumping. So the density also matters. The density varies, it will affect your pump flow and pump head. So here you can see the physics of fluid flow in pumping. Okay, so there is the equation, continuity equation, Bernoulli equation, then the Darcy-Weisbach equation for the losses. Then you have the minor losses through the valves, bends. Okay, by using this equation. Okay, this equation also you will get it in ASHRAE handbook. Okay, so there are three type of flow. One is the laminar flow, transition flow, and turbulence flow. Okay, and there is a velocity and pressure constraints for the water supply. So here you can calculate the hydraulic pressure, tank hydraulic hydrostatic pressure, pipe friction by using the equations. Whatever the equation we have seen, you can, and also you can check the velocity checker. Okay. Now the water demand estimation. How to calculate water demand estimation? Okay, so basically remember we calculate the WSFU. We start with the WSFU, right? So the type of water demand is based on the domestic demand, like you have a bathrooms, kitchens, laundry, drinking, intermittent stochastic usage, commercial demand such as offices, restaurants, hotels. Okay, so here you have a more continuous during operational hours. So for commercial application, you have a domestic application, you have an industrial application, then you have a fire demand application. Okay, so you have a physics perspective, like where water is incompressible. Total volumetric into a pipe is the sum of all simultaneous demands. Okay, so not all fixtures operate at once. Okay, so this is a probabilistic nature, right? Okay, then per capita demand, like for example, as per there are different standards. You can go with IPC, UPC. There are British standards, European standard. Then there are some local regulations. It will tell you that for the demand, okay, per day, liter per capita per day, per person, how much demand is required. So based on the demand, it's not, it is a general, but there are local standards. Okay, if you go to Dubai, we have a local regulations. Per depends upon the application, per day what is the consumption. Okay, so based on that you can calculate the consumption. So Q consumption determines this design flow rate. Okay, so the Q average is nothing but total daily average divided by 24 multiplied by 3600 will give you the design flow. Okay, so the average flow is insufficient for design because of peak usage. Okay, so that is why you cannot just calculate the total demand divided by 24. So this is like average demand. Okay, but as an actual, okay, so to calculate the peak or probability, you will use this type of calculations. Like see the WSFU. We start with the WSFU, right? So the WSFU is a dimensionless value that quantifies the probable simultaneous demand of plumbing fixtures. Okay, so it calculates the probability, what is the value, okay, for that. It's a dimensionless. It allows translation from individual fixture demands to system flow rates. Okay, so say for example, if you talk about each fixture have a different WSFU, that's what we take it from IPC standard. Okay, depends upon your applications, right? So here you can see based on the probability of simultaneous usage. Okay, can you see here the peak, for the P is equal these equations. Okay, like to calculate based on the fixtures, the probability that a single fixture is in the use at a given time. Okay, so the total demand Q probable equal Q maximum multiplied by DF. So factor. Okay, so the DF is a diversity factor. Okay, N is a scaling for large N Hunter formula. So here you can see the probability method. Okay, the Hunter curve. The graphical representation WSFU with probable flow. For a small number of fixture, diversity factor can be 1. If you have one toilet, then you can take as a 1 full flow. Okay, but the large installation diversity reduces simultaneous flow. So if you have a 10 fixture, will give you different flow rate. Not 1 is 0.3 and 10 is 3. Not like that. So the more the fixture, your flow rate or WSFU will go down. Okay, so the conversion to design flow rate. So how to calculate from WSFU to the flow rate? So that is the equation here. Q design equal K multiplied by square root of FU fixture. So how much fixture you calculate, based on that you will multiply by K. K depends upon the standards, typically 0.01 to 0.0015 for domestic application. That's a factor. So when you apply the factor, you can able to calculate Q. So whenever you see the IPC standard, you will find all the WSFU and WSFU value for cold water and for hot water. Then you can get the WSFU value. Then from the WSFU value, you can go to the flow chart. So based on the WSFU value, you can able to find the GPM. So that GPM, how it comes? It comes from using this equation. K multiplied by square root of fixture unit. So you have a fixture unit, you calculated multiplied by the K factor, depends upon the demand. Okay, depends upon the application and demand, your K factor, then it will give you the flow rate. So that is the way you calculate. So the peak factor accounts for hourly variation in demand. Okay, sometimes you may not go with the average hour. Sometimes you have to consider the peak factor as well. Say for example, like schools. Okay, so schools, maybe it will not be operated all the time average. Okay, suddenly there is a break. So what will happen? All the students may go and access the toilet. So there will be peak hours, right? And if you go to airport, maybe when some flight comes, when the flight sometime they landed, then the people started moving, leaving the aircraft, and they will start going to the immigration. Okay, while going through the immigration, they will find some toilet and they will try to engage, right? So that time the peak occurs. So like the peak will not be all the time same for all application. If you go to, say for example, office area, there is no peak because the people can go to toilet anytime, right? There is no peak occurs. But the application like say for example airport, or you can say like schools, uh, or something like that application, there will be peak flow as well. Okay, so that peak factor you can consider here. Say for example, when you talk about residential, there is a peak factor here. When you talk about commercial, there is a peak factor. Sometimes you have to calculate multiply by 2 commercial. Okay, industrial peak factor depends. Okay, so the minimum waste maximum flow rate. The minimum flow ensures continuous supply, prevents stagnation. Okay, the maximum flow avoid pressure drop, noise and erosion. So calculated using diversity factor, WSFU and the peak factor. Okay, so here you can calculate Q minimum, you calculate Q probable, Q maximum, right? So the Q minimum is nothing but 0.6 multiplied by Q probable, and Q maximum is nothing but 1.5 multiplied by probable. So this is all the equations. Okay. The flow velocity determines turbulence, friction and cavitation risk. Clear. Then the storage tank sizing. How we calculate tank sizing? Q peak hour multiplied by T storage plus fire dam and allowances. If you have a tank consists of both fire and water, then you have to add together. Otherwise, you have a separate fire tank, separate tank, and you have a domestic water separate tank. So domestic water separate tank, Q peak hour multiplied by T storage. Okay. Sometime your demand will be calculated based on per capita, per daily basis. Sometimes you calculate your peak hour multiplied by T storage. How many hours is required? Clear? And if you go to hydraulic retention, ensures water turnover, prevents stagnation and bacterial growth. Okay, so this is the reason we use circulation pump for the tank. Yeah, yeah.
Tea storage means what is?
It's a time. How much duration?
Okay.
Okay, say for example, sometime you may have to storage like office areas. Okay, so office areas usage will be, say for example, 10 hours, right?
Yes, sir, yes.
Because night time there will be no usage because it's office. So that application you will calculate for 10 hours, multiply by what is the peak hour demand. So multiply, you will get the total demand, V tank, the volume of the tank.
So the peak hour, can you give me any examples for that? Peak hour
Okay.
will be like 2 hours or 3 hours like that.
Okay. Q peak hour, can you see here? Q peak hour is nothing but P factor multiplied Q average hour.
Yes.
Okay. So the Q average hour is nothing but total daily consumption divided by 24 multiplied by 3600.
Yes.
So what is the total daily consumption? Say for example, if you talk about for domestic application, you have 100 liter per capita per day.
Okay.
Okay. So here actually there is a unit conversion. This is a liter and this is a meter cube. You can just convert, right? So how you convert? 100 divided by 1000, it will give you 0.1 meter cube per second, right?
Yes.
So this is a liter per day. Okay. So liter per day, you can just convert into liter to meter cube per second. That is why this conversion. So the total daily consumption 100 divided by 24 multiplied by 3600. Then it will give you Q average.
Okay.
Clear?
Yes. Yes. Yes.
Okay. So that Q average is here. Q average hour is here. Okay. So this is the Q average hour. Okay. So that you multiply by power factor, like the peak factor. So you have a different peak factor, right? Depends upon the application. Then you will get Q peak hour. So that Q peak hour you will be using multiplied by number of hours you may use. So that will be your V tank, volume of the tank.
Okay. Yes, got it.
Okay, so you can start practicing. Remember, we have done many classes. You know WSFE calculations. You know how to calculate GPM. Okay, so this is the steps. This is the actual step. How we calculate the volume of the tank.
Okay.
Okay, so say for example, there is an example also given here. residential building, you have a 5 WSFU, 50 apartments, so it will give you total of 250 WSFU, right? And for Q probable is nothing but 0.01. Okay, so that is depends upon the K value. So the K depends upon the application as well. Okay, so here you can see 0.01 multiplied by square root of 250, it will give you the flow rate, Q probable flow rate. Then the peak factor 1.5 depends upon the application. Residential 1.5, 1.5. It will give you peak flow rate. Okay, so you can calculate probable flow rate and peak flow rate. Okay, the daily consumption assuming 1.25 meter cube per day per apartment. Okay, so you have 50 apartment, it will give you 60 meter cube per day. So Q average is nothing but 60 meter cube per day. You can convert into Q average, right? Then you have a retention 6 hours. Okay, so you can multiply, you will get the volume of the tank, right? Clear?
Yes, sir.
Yeah. Start practicing, then you will get idea. Okay, then we can discuss. Maybe you can take one Excel sheet, take one project, and you can start calculating that. Then the water supply piping design. Remember we discussed before. There are different pipes have a different roughness. Okay, so because this roughness depends upon the smoothness. If your pipe is very smooth, then the friction is less. If your pipe is very hard, like a GI or some ductile ion, okay, so because inner that the surface is very hard, then your friction will increase. So that is also given here. Okay, so the pipe material, you can see the durability, chemical compatibility, roughness, temperature tolerance, cost and availability, right? It's very good pipe is copper pipe, for example, but you cannot go and buy for all application because it is a cost. Okay, and sometimes availability, maybe some material very rarely available, it's very demand, so that also you have to check. Okay, maybe very easy to pay high electrical electrical charges rather than to go with the smooth pipe, but the availability is very difficult, right? So these are all the things you have to consider to choose the piping. Then you can calculate the pipe roughness. This is the equation to calculate I will share you one Excel sheet how to calculate pump head calculation. Okay, so that based on these equations. So there's the F is the friction factor. Friction factor is here. L length of the pipe. V velocity square divided by diameter of the pipe 2G. If you apply, you can calculate Q HF friction factor. So that will be used for your pump head calculation. So you calculate flow rate and also you calculate friction head. Okay, here you can see the standards, piping, sizing standard, IPC standard, UPC standard, British standards. Okay, so here you can see one example, the velocity, right? And the physics behind velocity limit. There is a friction losses. Higher velocity, it may create turbulence. Then you have a high friction factor. Then you have energy loss increases. So you may have to pay more electrical charges. So you can see the Reynolds number. So there is a laminar flow. How you calculate laminar flow? If your Reynolds number is less than 2000. If your Reynolds number is more than 4000, it is turbulent flow. If it is in between, it is called transition flow. Right? Then you can see the erosion and noise. High velocity, it will increase pipe wall wear, cavitation and flow noise. So the cavitation occurs if local pressure drop below vapor pressure. So this is the P local lesser than vapor pressure. Okay, if you are low velocity also there is a problem. It will create a solid settle and pipe blockage. So your velocity should be very optimum. Not high, not low. Should be in between. So here you can use the Darcy-Weisbach equations, right? This is the equation. You can see the definitions here. Okay, then this friction factor derivations based on the physics. You can see how to calculate. This all just for understanding purpose. Maybe we will not use because we have a chart to use that. So for turbulent flow, you will use Coolbrook equations to calculate your friction factor. Okay, if your flow is laminar, then you will use direct formula here. This one, F equals 65 by RE, Reynolds number less than 2000. So this is very simple, 65 divided by RE, Reynolds number. But this equation is a little bit very complicated. But you have a chart. There is a Moody chart available. You can go and you can take the values here. Okay. Then also there is a Hazen-Williams equation to calculate your pressure drop. There is one method is Darcy-Weisbach equation. The another method is Hazen-Williams equation. Correct. Then another method is friction factor derivation. So which is simple, you can use it. It doesn't mean that you have to use all three. Okay, which is simple for you, you can use it. Then minor losses like based on the elbows, T's, this based on this equation. This is HM equal K by multiplied by V square by 2G. If you go to ASHRAE standard, there is a piping design. So if you go to the piping design, there is a K factor for the fittings. And normally the K value is there. Based on that, you can calculate your minor losses. So then the pressure drop across piping. So these are the equations here. Total pressure drop between 2 points. So delta P equal rho G HF plus HM plus delta Z. Right? So what is HF? Here. This one. Darcy-Weisbach equation. Right? Then what is HM? HM is the minor losses. Plus delta Z elevation. Because this is an open pipe system. Chilled water, we don't use delta Z. We use only HF plus HM. But for open pipe system, you will use delta Z as well, elevation. So you can calculate your pressure drop across piping system. So then you have a loop, branch, manifold. There is a branch system, loop system, manifold system. Okay, single pipe splits into branches. Okay, and if you have a loop system, multiple parallel paths, pressure more uniform. This is like a looping system. Okay, then you have a manifold. You have like a central distribution. Okay, then you can see one of the example here, how they calculate the pressure losses, determine pipe area, A equal Q by V. This is a continuity equation. You can calculate the area, determine diameter, D, diameter. Then the friction loss, you can use HF by using these equations. So K factor multiplied by V square, velocity square, divided by 2G. Okay, so this will give you the friction factor, this equations, using these equations, diameter 2G. Then when you talk about pumping system, you have a booster pumps, transfer pumps, then jockey pump. Jockey pump is nothing but you can say it's like a pressure maintaining pumps. So here you can see the pump head calculation, the same thing, static plus friction plus minor losses plus elevation. Okay, static head, how to calculate? Sample here. Whatever we discussed, the same thing. The friction losses calculation, elevation gain, from the discharge to suction, what is the difference? Discharge to suction, what is the difference? Your discharge will be somewhere here, your suction will be somewhere here and discharge will be somewhere. So what is the height? Okay, so here you can see the worked example. Friction, how to calculate the friction value, minor losses, static head. Then you can calculate total dynamic head. Okay, and then also you will check whether net positive section head or not. Okay, so here there is the equation P atmospheric divided by rho G plus H section minus H friction minus PV by rho G. If you apply this equation, you can calculate NPSHA. Minimum NPSH needed by pump to avoid cavitation from pump manufacturer. So this value will get it from pump manufacturer. Okay, so what is the physics? Water vaporizes. If local pressure drop below vapor pressure, then cavitation occurs. There is a bubble formation and implosion that will damage the impeller. Clear? So the cavitation physics, P local always should be lower than P vapor pressure. It's too high, causing pressure drop. Okay, the vapor bubble collapse in high pressure zone, shock waves, impeller erosions. So that is why we use, always we check that, we do the check. Okay, NPSH check. Then you can calculate the pump power by using this equation, simple equation, rho G Q H TDH. You know the pump head, you know the Q, you know the G, you know the rho. Calculate the pump hydraulic power. Then shaft power divided by efficiency. You will get the shaft power, right? Then you have a pressure zones, PRV, okay, pressure reducing valves. So the pressure reducing valve, where you need a pressure reducing valve, you have to calculate that. Okay, this is a hot water system design. We can study after some time. Once we thorough with uh, uh, domestic water application, the normal cold water application, then we can go to uh, hot water. I will explain you based on ASHRAE standard. Okay, then here you can see circulation pump. Circulation pump to avoid any uh, solid, any stagnation. Okay, if the water is stagnant, there is a chance of bacterial growth, there is a chance of scale formation. That is why. Okay, this is a cold water storage system. Okay, so this is the equation, like how we calculate the storage. I think we have calculated before. V tank is nothing but daily usage multiplied by R factor. Okay, so then there is a transfer pump, booster pump. Okay, there is a standard, same thing. Whatever we discussed before, the same equations given here. Okay, so this is a water hammer arrestor. Why the water hammer is required? Remember last time we calculate based on the WSFU, you will choose the model. Okay, but what is behind the water hammer arrestor? There is a pressure, surge pressure. Okay, that surge pressure will be absorbed through the water hammer arrestor. So that how to calculate surge pressure by using Joukowski equations. Delta P is nothing but rho alpha delta V. So here it's given here. What is delta P? Surge pressure. Rho is density. A is a wave speed in pipe. Okay, delta V is the change in flow velocity. There is a sudden close will change in velocity. There is a, say for example, you have a velocity of 1 meter. So the water is flowing 1 meter. When you close, what will happen? Suddenly the pressure, the velocity will increase because it will, there is a pressure increase, right? Because you have a close. So that is a change in flow velocity, right? Okay. So then you can see that there are some worked examples here. So whatever we discussed before, you can see that worked examples like WSFU calculation, calculate total WSFU, probable flow demand, piping sizing, how to calculate the pump selections, how to calculate cold water storage calculations, how to calculate the flow, full building water supply design example. All it is given here based on the standards, right? So this guideline will give you the overall picture for the water supply design, okay, based on the physics explanation. Clear?
Yes, sir.